Welcome back. So we talked about relative dating. Let's talk about absolute dating. Why does it always do that? So with the discovery of radioactivity, which is in the late 1800s, early 1900s, Marie Curie was kind of leading the charge in that. With the discovery of radioactivity, it really destroyed Lord Kelvin's argument about the age of the Earth and the cooling rate. Because radioactivity helped to provide a clock to measure Earth's age. In fact, specific age, absolute age, I should say. So, radioactivity, so a little chemistry again. Radioactivity is the spontaneous decay of an element to a more stable isotope. More in just a little bit. When an atom decays from one element to another, usually heat is given off, which helps to explain why the Earth is still warm inside. There's radioactive material all throughout the layers of the Earth, and as these materials decay spontaneously, heat is given off. So Kelvin didn't know that there was also this continual heat source, not that the heat was there from formation and just started to go away. But now radioactivity provides geologists with, a tool to kind of measure the exact ages of rocks in past geologic events. Excuse me. But understanding absolute dating, we have to kind of go back to talking about atoms and isotopes again, just for a little bit. All right. Isotopes, and we talked about this, last unit. So isotopes are different forms of a particular element. They have the same number of protons. But they have a varying number of neutrons, which then causes them to have a different atomic mass. So again, the big thing with isotopes, they have different number of neutrons, same number of protons. Remember that how many protons defines what material, what type of element you are. So if an element has 6 protons, it's carbon, regardless of how many neutrons it has. So that makes up the different isotopes of carbon. All right, because if it has 7 neutrons, it's carbon 13. 8 neutrons, 6 plus 8, carbon 14, etc. So, but these isotopes are important in radiometric dating and thus absolute dating. Most isotopes are stable, but some are unstable, meaning they just spontaneously give off material. Not all isotopes are unstable, some are fine, but those that are unstable are useful because they give off material at a certain rate. So we use the decay rate of unstable isotopes to determine the absolute ages of rocks. So if there is an isotope of a particular element, through lab and scientific discoveries throughout the past 100 plus years, we figured out there's a number of isotopes that break down spontaneously, and we've also figured out the rate at which they do that, how often they get rid of material. So we use the decay rate to help us put an absolute date to rocks and geologic events. So let's talk about radioactive decay. It's the process, again, by which unstable atomic nuclei, the nucleus of an atom, protons and neutrons, spontaneously transforms into an atomic nucleus of a different element. Because if we're getting rid of or adding protons, if we're changing something about the nucleus, then we're changing the element to something else. We're transforming. There's 3 different types of radioactive decay, alpha, beta, and gamma decay. More on that in just a second. And again, as this decay process occurs, heat is released, and that's what is continuing to keep the interior of the Earth hot. That and the leftover heat from the formation that was kind of locked in as the crust of the Earth cooled. But since we have this radioactive material, it's also providing heat. So the interior of the Earth is going to remain hot for probably a long time. Spoiler alert, in probably about 5 billion years or so, the sun is going to grow and swell and envelop the Earth and a number of other planets, and that's what's going to do away with Earth. The interior heat will probably still be fine even 5 billion years from now. But in any case, again, that heat is just a byproduct of this decay process. So in alpha decay, what's known as a parent isotope, when it undergoes radioactive decay, it gets rid of two protons and two neutrons. So again, if we're losing protons, we're changing the number of protons in what's now known as this daughter isotope. So different number of protons, different element. In beta decay, the parent isotope, the original material, as it undergoes decay, a neutron spontaneously turns to a proton and gives off an electron. So if a neutron turns to a proton, then we're adding a proton. So again, we're changing the number of protons. So now we have a new element, a different element. And that's the daughter isotope. The parent is the original stuff. What it decays to is called the daughter. Gamma decay, we don't really have to get into too much because to understand what we need to, we just want to focus on alpha and beta decay. So again, alpha decay is when two protons and two neutrons, which is known as an alpha particle. That whole bundle is called an alpha particle. So we have an alpha particle here, is emitted from the nucleus. We're getting rid of two protons, so we're changing the number of protons. Therefore, we have a brand new element from the parent to the daughter. Beta decay, again, a neutron spontaneously emits an electron, and in doing so, it changes to a proton. So now we're adding a proton from the parent to now the daughter. If we're adding a proton, we're changing the number of protons. Therefore, we are changing the element. So it's a brand new element. So in both cases, a change in the number of protons creates new elements in this decay process. Some isotopes of particular elements only go one decay step before they become stable. They were unstable, they undergo one step of decay, and now they're stable. For instance, rubidium-87 decays to strontium-87. Potassium-40 decays to argon-40. But other isotopes undergo several decay steps. Uranium-235 decays to lead-207 by 13 decay steps. Uranium-238 decays to 206 by 14 decay steps. These large numbers after each of these elements is not the atomic number, but the atomic mass. So let's take a look as an example of U-238 and the 14 decay steps before it finally reaches stable lead-206. Okay, so here's U-238. It undergoes an alpha decay, so it loses two protons and two neutrons and becomes thorium. And then, I'm kind of hidden back here, and then it goes a beta decay, so a proton is added, but an electron is lost, and that changes it to protactinium, and it goes another beta decay to change it to U-234, and these are all unstable, which changes to thorium-230, which changes to radium 226, which changes to radon 222, which changes to polonium 218, which changes to lead 214, not 206. Then we undergo beta decay again to bismuth, back to polonium, back to lead 210, still not lead 206, back to bismuth, back to polonium, and finally one more alpha decay to lead 206. Now the rate at which they go individually to these different elements is all variable. It might only spend a fraction of a second here, it might spend 1,000 years here, but overall, this whole process, we know this whole process, we've done this and measured it in the lab, we can figure out the whole process that takes it from U-238 to 206 at a particular time frame. So going back here, we know the time frame it takes rubidium-87. We know the one decay it takes to get to strontium-87, potassium-40 to argon-40, U-235 to lead-207 in 13 decays. We know that whole time frame. We also know the individual ones. But knowing the original parent and all the way to the stable daughter, that whole time is a useful amount of time, and using that decay rate from the original unstable material to the final stable daughter product, if we know that time, and we can look at a particular rock sample and we can compare how much original parent material there is to stable daughter material there is, knowing how long that process takes, we can put an absolute age to a rock. Sounds complicated. We'll walk through some examples. So we're going to pause here, and when we come back, we're going to talk about half-life and how that informs us or helps us figure out the absolute age of rocks. So this is just part 1 of this section. The next video will be part 2 to continue this conversation. I'll see you back there in just a second.